Hey everyone, thanks for the intro. My name is Rhys Arkins from WhiteSource. My day job is Director of Product Management, but I spend about half of my week working on open source and some of WhiteSource's open source projects. And so I put together this presentation as a bit of a cross between what we do and my passion for open source, talking about unsolved problems in open security. The goal was to cover some of the things which aren't greatly solved, which no company or vendor has a great story for yet, both just out of interest, but also as awareness, and maybe some of the people in the audience that see these types of presentations might be inspired to solve it one day as well. So I'll jump into the slides now. Okay, so one of the things which I really like about open source security is the aspect that it is often quite underestimated by people. Using this classic iceberg model, there's around 60 to 90% of deployed code is open source these days, whether people are building APIs, building websites and things like that. So what people often see really is the code that they write. What they don't think about so much is the open source code that also ships with it. For the consumers of software, whether it's end customers, whether it's free or non or paid, either way, their view of it is that like what you ship is your responsibility, whereas people tend to have the idea that what they write is their responsibility. So people definitely underestimate the responsibility that comes with using open source, especially from a security point of view. Something else which makes open source security really different to most security, I would say, is the fact that it's a very public thing. So a favorite phrase of mine is the enemy always gets a vote. So people say, oh, this is not my enemy. Well, your enemy also gets a vote in that. And if they're your enemy, they're your enemy. So with open source vulnerabilities, the disclosures are public and the clock starts ticking right away. So when you might discover a problem in say the API you've written, and someone might point out, hey, you know what, if somebody figured this and this and this out, they might be able to impersonate another user or access some other. And you might think, okay, well, let's fix that on the next sprint or something like that, because in the next version, because that's going to be complicated, and the chances that someone would figure that out is pretty low. With open source, it's quite different because it's out there. So generally, when you find out about a vulnerability, like a CVE, then it is public. And so it starts ticking. So there are people that are, on the black hat side of things, who are looking at the 0-day vulnerabilities, the CVE announcements, and they might react quite quickly to try to find it. So people don't really have a vote about whether they just decide to ignore open source security or not. All right, so just to set the level sets, this topic, of course, is unsolved problems, but I want to talk about, well, what are the solved problems then, just as a comparison. So the first one that I call mostly solved is knowing what open source you're using. There are tools for this. There are open source tools. There are commercial tools. In general, this is mostly solved. If we look at dependency maturity levels, in the old days, using open source or using other code was like the, we'll call it the Stack Overflow approach, right? Copy, paste, commit. You take someone else's code, you copy it in. And that was actually how it worked. People used to post, say C++ libraries on their personal website and say, if you're interested in using it, download it and use it. You would actually copy and paste it into your project. People got a little bit more mature and started having like build scripts and shell scripts that would copy in the data as part of the build rather than necessarily committing it into the repository. Of course, the next step was package manifests. So this is things like your package.json in npm, your pom.xml in Java. And then the fourth level of maturity these days is log files. So for the package managers that support them, being able to lock all of your dependencies gives you like a deterministic build. It means that if you run like npm install or bundle install now, and then with the same commit of code 6 months later, because you wanted to reproduce something, you run it again, you would get the same result. And you can't say that for a lot of package managers which don't have a lock file. So for example, if you just run Maven install or Gradle install, you will get a set of dependencies that are up to 6 months newer than the ones you got in the previous 6 months. And in fact, maybe your project doesn't even build Right. So in terms of maturity levels with dependencies, package managers with log files is kind of the standard these days where it's available, and I strongly recommend that you use them. Languages and log files. So at the best at the top here is like JavaScript with npm yarn and pnpm. You've got Bundler and Ruby, which is one of the first to have log files. Composer and Go modules uses checksums, which is similar. Good Poetry and pipenv using log files, but they don't quite have the same flexibility. They don't reliably reuse the same tree if you do any upgrades. Less good is definitely the Java managers, Gradle and Maven, because those it's not common to have log files and they're not natively supported, so the majority don't use them. Okay, so then moving on to detection then, like I said, knowing what open source you're using. There's two approaches to it. I call these face value and forensic. So with face value, that's where you look essentially at the package manifest, the log files. So the project declares its dependencies and you take them at face value. That's what you're using. So you take those files, you pass them, you say, great, I know all your dependencies. I even know your transitive dependencies. The forensic approach, and this is more in the commercial tools like WhiteSource producers. In this case, it's where you absolutely must know exactly what has gone into your software. So in these cases, what you'll generally do is you'll run your build scripts. So run, for example, your CI that pulls in dependencies with package managers, but also maybe through other means, such as inside Docker base images and things like that. Then fingerprint every file in the build and post-build directory and compare them to a known database of open source files. This is the forensic approach of knowing like really exactly what you're using. So anyway, this is the first step. This is like knowing what open source you're using, and there's different levels of convenience and speed that you can do in order to do that. The second sort of solved problem in open source is being alerted when your open source has problems. So in terms of security notifications, automation is really essential here. If you are doing a manual process to check for problems in your open source, there's a very good chance that you will forget, you'll go on holiday, or something will not work properly. Really, this is the type of thing that has to be automated to be reliable. So the ideal system, it knows what open source you're using at all times. It also knows what's vulnerable at all times, and then it correlates those two. So this is also important because if you use only a scan-based approach, then it means if there are new vulnerabilities, you don't know about them until the next time you scan. Whereas the ideal approach is more like a cross-matching, where every time you scan, you might potentially update your manifest list. But even if you haven't scanned recently, that manifest list will be crossed against vulnerabilities. So these are these first two steps, knowing what you're using and knowing if there are problems. The third solved problem, vulnerability remediation. So the good news here is that 85% of CVEs in the main NVD database that are released these days are announced with a fix available. So it means if you've got npm packages, PyP packages, things like that, by the time you are being told that there is a CVE that affects you, there's already a version available for you to update to that's already fixed. So this is a great thing that is quite different from, we'll call it the olden days, where people would be told there's a vulnerability with no fix, and they might tell you what line of code it's on, or you might have to monkey patch your dependencies. So remediation has become simpler by the fact that you can upgrade to a stable version. Okay, so those are the three fairly solved, mostly solved problems in open source. Now I'm going to get to the much less solved ones. So starting off with unsolved, one that people talk about a lot, it gets a lot of attention, is the idea of identity and reputation in open source. People think that a lot of problems in open source could be solved, if we had like reliable ways of knowing who produced it, signing your work to show that it was definitely you that did it, and things like that. But it's important to understand security is not just CVEs and vulnerabilities. So let's look at the difference between vulnerable versus malicious packages. So vulnerabilities, which is pretty much what I've been referring to until now, these are like your general CVEs, your typical. They're an accident, they're an oversight. Someone accidentally didn't close a string, or there was a regex problem. Often these are not even just an oversight. They may even be that the person that wrote that package had no idea about DDoS attacks in RedJOS or even what SQL injection is. That can happen as well. But essentially, they're an accident, they're a mistake, they are unintentional. The other thing that characterizes such vulnerabilities is that in most cases, they are not easily exploitable. There's multiple things that have got to go wrong. Just the fact that you're using a version of a package with a vulnerability, and that there are attackers that also know about this vulnerability, doesn't mean that you are exploitable. They have to discover you, they have to be able to determine that you're using it, and they also have to figure out a way to kind of, activate the payload, we'll say, to actually access that vulnerable code in a way that actually lets you be exploitable. So the combination of these means that although there are a lot of vulnerability alerts in the world, most of them are not exploited because it's not so easy. Malicious packages, in a way, are very different. Malicious packages are closer to viruses or worms or malware. Their goal is to intentionally do bad things, and often the goal is to do those bad things immediately. So this is a very different kind of security posture. And if you think about identity and signing, then just because you are who you say you are, the problem in open source is that if the only thing you say you are is like hotdog79 on GitHub or something like that, that's not actually telling you too much that makes you more secure. So then classifying malicious packages into two different categories is also important from a security point of view. So you have malicious packages which are bad from day one. An example of that one is typo squatting. So in typo squatting, somebody intentionally creates a package that is very similar to another package, like a keystroke difference, maybe adds an S to the end or takes off an S or something like that. And their goal is that people just install it accidentally. So maybe it's like, this is not a real example, but someone might release low space dash instead of low dash, one word without low hyphen dash instead of one word low dash. So they hope that someone one day types npm install low hyphen dash. That's an example of typo squatting. Now that's not going to do very much. So those are the type of ones where their goal is like a worm or a virus, just to get you to click on it, get you to install, and they will be bad from day one. Dependency confusion was an attack that was announced by like a researcher earlier this year, and that's an example of where they intentionally get you to install a package that you think is your package. It might be called Siemens-API on Ruby gems, but it's actually a package which is trying to trick you to install it, and then it will exploit your system. So that's category one, which is bad from day one. Category two, in a way, is much more dangerous. This is the idea of good packages turn bad. So this can happen because, for example, the maintainer of a package, a popular package, gets their credentials compromised. So they might have reused the same email password between some leaked exploit and npm or Ruby gems. Also, another example of this happening is a new maintainer takes over a package with malicious intent. So there's been cases where a package which is fairly popular but unmaintained by the original author because they don't use it anymore, someone comes along and like fixes a bug or two and then says, hey, you want me to help maintain this? And the original person sort of says, maintain it? You can own it. Here you go, take it. I don't want it anymore. So that's another example of where like a package that was totally benign can get taken over by someone new. And they can then add malicious code to it. The third way is when a package creator could potentially play the long game, where they create a package themselves with the intention to use it later as an exploit. We saw that actually in the crypto space, where somebody cleverly released an open source package which was useful, very useful for people writing cryptographic wallets. And then what happened was eventually one day they worked out a certain wallet that was using their library. They used the library because it saved them time compared to writing it themselves. And then they added in code that targeted users of that wallet and stole their Bitcoin addresses, and then actually stole a lot of cryptocurrency. So this is some types of malicious packages. if we go back to that identity, and you sort of see that like identity isn't going to solve a lot of those problems, because the idea of identity is kind of like, who are you, and can you prove it? And like I said, like, who are you in open source is often, hot dog 79 or something. That's not going to help you assess the reliability of that. And we don't want to make open source so that the only people you trust is Microsoft, Google, and Siemens and things like that. That would reduce the pool of open source we can use greatly. It's instead useful to look at the risk and reward. So package compromise rewards are mostly predictable. The goal is stolen credentials. That's what they're trying to get to: stolen data, stolen credentials. But the risks are quite variable. So for example, if you've just stolen someone's credentials to their Python, Ruby, or npm publishing, you don't really have much to lose except the credentials themselves. Like, you've got them, you publish something bad with it, it'll get discovered, and then of course those credentials get revoked and you've lost them. But you haven't really lost too much compared to when you started. Whereas for a malicious maintainer, where you've put all this work into building up packages, you've built up a reputation, then you've got a lot more to lose, because you're basically burning your legit identity by publishing something malicious. So focusing on two-factor authentication is by far the low-hanging fruit, and would provide a lot more benefit than the ideas of verifying identity and signing. It's essentially just making sure that the person truly has control of the account. The challenge, though, with two-factor is partly with transitive dependencies. So even if you have 10 dependencies in a project and they all have two-factor authentication turned on, there might be 500 or 1,000 total dependencies installed. And if only one of those gets compromised, then it's just as good as if any of them get compromised. So that's one of the challenges, is that you really need two-factor authentication all the way down, not just with the ones that you select. The other challenge is that two-factor authentication isn't well supported with publishing automation. People writing open source want to have reliable and automated ways of publishing. And so, for example, if you look at npm, you can have npm automation tokens, and they literally they disable two-factor authentication so that you can publish automatically. So, for example, you would see a lot of accounts might have two-factor authentication, but then they are using, they're using an automation token to publish, which then defeats the purpose. So this is not a solved problem, but as an example of an attempt to solve it, Google have the concept in npm. They call it wombat dressing room, because npm has a wombat mascot, and they open source this, and the idea was that you could kind of have a two-step publish process, so that you could say the automated bit publishes it into like a holding area, and then you can kind of give like a second step of approval for that, put in your two-factor authentication, and the tool uses that to publish it. So that one is a good example of trying to overcome this security challenge of two-factor authentication with automation. There's also another one to watch, is a project called SigStore, again, actually by Google. And this is Google's attempt to take on the signing and verification part. They've really looked into how to make it kind of lightweight. They have put a lot of thought into it. And if you're interested in these things, I do recommend checking out SigStore and Wombat Dressing Room as possible ways to increase your security. Okay, so I touched upon this quite a lot just before. Really big unsolved problem: malicious maintainers in open source. So if you look at malicious package creators, this is a much narrower, much smaller concept. So a malicious package creator, they develop a package with the intent to compromise it once it's popular. I mentioned it before with the cryptocurrency. It takes a lot of skill. It takes a lot of long-term planning. That's really playing the long game. It's not very common, but if someone's going to do it for a high reward, it's very hard to stop. What is much more common and hopefully easier to stop is a malicious package maintainer. So this is someone that contributes to an existing, ideally unmaintained package. They get added as a maintainer, they maybe even become the owner, and then they exploit the package. And the most well-publicized one of this was Event Stream. There may be other ones that have not been discovered as well. So this one is, there are of course some better ways that you can you can test for this, such as change of ownership and things like that, and treating packages which have changed the publisher with a little bit more skepticism than ones which have not. Right. But what's important also to understand is security multipliers from malicious packages. So a really important question to ask is, why can packages do so much harm once they're installed? Why are exploits hard to detect? Like we detect viruses pretty well these days in emails and stuff. Why don't we do a good job in open source? And then finally, why do exploits propagate so fast? So this is 3 questions now I'll cover in Unsolved Problems. So the first is the idea of sandboxing permissions. So open source packages should have less permissions. With quite popular ecosystems like NPM and like Ruby, you essentially allow almost unlimited code to be run on your computer the second that you install a package, because of concepts of post-install scripts. You don't even need to be using the package for it to be able to run arbitrary code on your computer. So it is language dependent. Some languages are much better at this, but essentially the packages can exploit either when they're loaded or when they're even installed. But if we think about the types of things we're installing, it might be a package to help you with crypto, to speed up a calculation. It might be some other string manipulation library, things like that. Neither of those need to access the file system. They don't need to access environment variables. They don't need to access the network. Yet that's exactly how the exploits generally work, is that somehow you're tricked into installing them, and they go and they read things off the network, they read things off files, they send things off. These are all permissions which they never needed or should have had kind of in the first place. So to think how to solve this one, it's best to think about operating system malware. So Windows especially, we'll say. So operating system malware is much less of a problem today than it was before. The answer was not that scanners got better at detecting bad apps. The answer was the concepts of zero trust and sandboxing. And apps then by default got only the permissions which are safe, which are needed, and any other further permissions needed explicit approval. And it also meant that the operating system stops them from accessing things not approved for. Probably iOS is the best in this example, but there's been great improvements across all operating systems by essentially identifying permissions that apps shouldn't have, and stopping them from accessing things which they don't explicitly declare that they need. In terms of open source, this is really the way we need to go as well. So an interesting one to look at here is Deno, D-E-N-O. It's an anagram of Node, created by the creator of Node. And he's gone for the approach of secure by default. Modules and apps need to explicitly declare and be granted permissions. So if you start an app that just goes and accesses the network or tries to open up a server, it'll actually get denied by default if it hasn't declared and had you approve the capabilities of it. That doesn't completely solve the problem for open source, though, because we have this tree of open source packages. And although your app might need to access the network, you may not want that particular dependency to. So another really interesting one to watch, this is Node.js only, but it's called Lava Mode. It's actually written by people in the area of crypto. And Lava Mode actually does attempt to essentially sandbox all of your dependencies and let you specify and approve which ones have what type of access, such as access to global state, access to network, access to file system, and so on. Okay, next problem, detecting malicious updates. Why is it so hard? So why are malicious updates missed? Someone adds bad code, obviously bad code, to an open source package. Why is nobody noticing? So the problems are generally that there's too much to review, it's too hard to review, and you actually can't really be sure that what you're reviewing is correct anyway. In terms of too much to review, the majority of software projects do not have the resources, like even companies the size of Siemens generally do not have enough people to read every line of open source which is in use. Feel free to correct me if I'm wrong on that one later. But as an industry, people have this assumption, even though they know that it's not possible for them to look at every line of open source code, they have this assumption that surely someone else has looked at it. There is this statement that comes out of Linux: given enough eyeballs, all bugs are shallow. But the challenge is, are there eyeballs looking at it? Just because something is open and open source doesn't mean people are looking at it. There are many lines of open source, even popular lines of open source, where the only pair of eyeballs that's ever looked at is the original authors. All right, so the next thing is why there's too much to review. It's too inconvenient to review. So if you think of, I understand you use GitLab mainly, you think of GitLab and you get a pull request from a developer. Maybe it's a pull request from an automated tool that says update your dependencies. Now, what you see when you're reviewing that merge request is like a single line diff. Version 100 changed to 110. You might get release notes, maybe. But the thing is that really it's not that line of code that says 100 or 110, which is the potential threat. It's what is coming with that new release. And reviewing that code, it typically requires going into some other system. So if you say, okay, I'm going to look at this code, you have to leave GitLab or whatever to go find a way of looking at that code. There's no major open source registry, like not npm.js, not Maven Central, and things like that, that supports a native diff of packages. So if you go to the registry and you say, I want to know what changed between these two versions, like for real, not in the actual tarball, none of them support it. The other challenge is that even if they did, many language registries contain built code, post-built code. So it's like jar files, it's Babel compiled JS. So it's very hard to really look at, as a human. So it is hard to review. Next problem is that if you go and try and look at the source code, like what's typically on github.com, like what you are downloading, the risk to you may not actually be what is on github.com. So, if you can't really look at that post-compiled code very easily, then you might try to then go and look up the source on GitHub. So the good news is that most of it is there. The bad news is that if there is a malicious maintainer adding malware to a package, they're not going to go put the malware on GitHub. They're going to put something on GitHub and something else on like NPM or on Pipey or RubyGems. The only exception to this is Docker Hub Auto Build. But apart from that, no major registry actually enforces or verifies the link between source and artifact. So every time you go to a package registry and there is like a link to the source, that's just like alleged source. That's not for sure the actual source. It could be completely different. Most of the time it's not, but you've got to think of what a malicious person would do, and they're not going to put their malicious code out in the open for you. The solution to this one is reproducible builds. So in this case, ensuring the verifiability of source code is a big missing link in open source security. So once it's done, it doesn't really require too much extra work, and it greatly decreases security risk for all involved, including open source developers. So the idea here is that you do have like a verifiable link between like a commit in Git, for example, and the final published tarball, and that you can verify it. Now, although you may not verify every single release, the fact that it is verifiable greatly discourages anybody from maliciously attacking that package, including you as the developer of the package, because what they know is that if they were to try and like compromise your laptop, a phishing attack on you to get access to your open source package, that if they published a compromised version of your package without also publishing it to GitHub, then it would fail the reproducible build and would be caught very quickly. So reproducible builds decreases the risk for everybody, including even the producers of open source. Now, one to watch here, I added this one recently, is actually from WhiteSource. It's WhiteSource Defend. We acquired this about a month ago. I found this solution after first creating these slides, and we decided that we really wanted it in-house. And it actually is the one exception to what I mentioned before. If you're on RubyGems, there is actually a link that says view differences between versions, and that view link goes to WhiteSource Defend, which has diffs between all of the versions. And it's actually pretty useful in terms of reviewing new packages. It also has a bunch of other stuff like automated detection of malware and stuff, but from an open source user point of view, a great benefit is the diffing part. All right. Decentralized versus centralized registries. I call this one undecided because it's not necessarily a problem. There is this idea that, open source, everything open, we should have decentralized registries instead of like companies or things controlling a centralized one. But all things being equal, decentralized makes security worse, right? Whenever a malicious package is discovered, all the ones I mentioned before, the first instinct from everybody, apart from, well, this package needs to be deleted off the registry, is why didn't the registry detect this? Like, how long did it take them to remove it? This is how everybody reacts when there is a malicious attack on a registry. Yet a lot of those same people have the idealized idea that we could have like decentralized registries where no one controls it. But if no one controls it, then it makes it quite challenging to yank things or to know when things should be removed. So centralized blocking or revoking of packages can't be done in a true decentralized approach if there's no one in control. So detecting Git-based dependencies has some advantages if the source is verifiable. Like GitHub, for example, if you use GitHub to host the source, then they probably would take it down if it's malicious, but that's not really like their primary goal. Okay, now back to unsolved is malicious package propagation. Why does malicious code propagate so fast? One word, semver. Because people, when semver, this idea was created, people said, okay, if it's x.y.z, all releases with the same x should be compatible. Therefore, free upgrades, free bug fixes. I just always install the latest x. And that's basically how people use semver today. The majority of package managers, npm bundler and maven, for example, they take a very optimistic approach to version ranges. So if you ask them to install a range, they'll install the latest, the latest x, latest version 1. Now, lock files do help here, but you do need to unlock your lock files and refresh them sometimes. And then the problem just comes back again because, at the time that you refresh and update, you're going to update to the latest versions, some of which could have problems. They could be propagating malicious. So an example with semver, let's say your code depends on a package called red version 1. Red depends on package blue version 2, and blue depends on orange package orange version 3. Now, without changing your dependencies, which is red version 1, a new or a malicious version of orange could be installed. So you've pinned your dependency, but orange updated to a new version 3 and it had malicious code. Also, even though you've got a log file, just think you might start a new project and you say, okay, yeah, I'm going to use red 100. That's what I'm using my other project, and you install it. So even if you had locked your first project, you start a new project, install red 100, and you get the malicious orange. So this is an example where ranges do the opposite of protecting you. In short, uncapped version ranges are an anti-pattern. So by uncapped, I mean any new version within the range is compatible and you should use it. The alternatives to uncapped version ranges is to cap them. So instead of, for example, saying 1.x, you use, greater than or equal 100, less than or equal to 140. And that would mean that if like version 141 gets published, you don't just get it installed, the first time you run npm install. So that's option 1, is to use these complex ranges. Option 2 is minimal version selection. Go modules is completely different from pretty much all the other package managers. They have a concept of minimal version selection. It still relies on semver, so it's not strictly semver that's the problem here. Go doesn't ask you to put ranges in your Go modules definition file. So they know that if you have version 100, it should mean compatibility with any 1.x. But here's the difference. Go modules won't install a newer version than you need. So if you say version 100 and up, it will install 100. It won't install version 141 until you or another package in your tree says that 141 is the minimum necessary version. Now, what that means is that any malicious release doesn't get propagated automatically. Because, if version 141 is the malicious version, it won't get installed until some other package says, I need 141. Right? Right. So in terms of version selection, the way forward, this one's pretty tough. This falls into the really difficult unsolved problems category. So the short-term thing is to use capped ranges and bump them regularly. So this, where was it? This one I mentioned, 100 less than equal to 140. This way you do not get new versions instantly, that you have to opt into them by, bumping that range higher and higher. A more long-term problem is to use minimal version selection and then bump when necessary. What this means, though, is you don't get these automatic bug fixes. If 141 is actually a handy fix to an important bug, you, as the package that depends on it, would need to say, you know what, only use 141 and above, not 100 and above. Right. And that also means that important bug fixes require bumping of the minimum version. All right, so just wrapping up, there's a few key points and takeaways. Part one is better open source publishing protection. So really, single-factor authentication is unacceptable. It should be unacceptable in the whole dependency tree. It is very hard for the registries to really play the leading role here. They need two-factor authentication capabilities and the ability to enforce it. But it's really up to the consumers of open source. It's up to like big companies like Microsoft, like Siemens, to prefer packages which have two-factor authentication all the way down, and really let the market push open source publishers where it's like, no, we'd love to use your package, but you don't have two-factor authentication enforced, so we cannot. So this means the registry needs to support two-factor authentication. It needs this, like, we'll call it consumer pressure. The second part is verifiable source code using reproducible builds. I think this will be the biggest shift in open source security over the next 5 to 10 years. There's no point reviewing for malicious code if you're looking at the wrong code in the first place. So looking on github.com doesn't help you today. Non-reproducible builds should be a code smell, like the lack of two-factor authentication. That if there are packages which can't be reproduced, again, that should be a reason not to use them if there are alternatives. So again, it needs the industry support for tooling. It also needs really the adoption of reproducibility mindset. Reproducible builds is far behind two-factor authentication in this area. Number three, open source dependencies should be sandboxed. It requires a lot of work on the language size, but today's approach to malicious open source packages can be really compared to like Windows 95, pre-malware tsunami. We are just begging to be exploited at the moment because of the fact that there is no way to contain the permissions of any package you install or any of the packages that it brings with us. Unfortunately, there's no relief in sight for language ecosystems. It needs a really large re-architecting of language package imports. And I think it'll only happen if you see languages like Dino get adopted for the security reasons. And the final point is package managers implementing minimal selection, just like Go modules has. So in my opinion, it is madness that a malicious package can be released and within minutes be on systems and exploiting them. We don't have a need to have packages minutes after they're released unless you intentionally want it because you know that there is a bug fix in it or something that you need. So the fact that you can get it minutes or seconds without anybody reviewing it is quite crazy. Minimal version selection should be a configurable option for package ecosystems, but it is going to require a lot of work on the package manager. It's also going to require a lot of awareness. All right, that is it. I hope I left enough time for questions.
Yeah, sure. Hey, thank you, Rhys. And yeah, I guess we are going to check out the questions that we got from the audience. And the first one is there a tool method to list the permissions required by NPM packages?
Yeah, it's a really good question. So this one that I pointed to, Lava Mode, it's actually like a number of tools in one. And one of the tools they have is like a visualization one where you can, it does extract out what packages are trying to access and then gives you kind of like a view, and it uses colors to identify risk. It's not a very widely adopted package. It is quite amazing some of the things it does. So I'd recommend checking it out for NPM for sure. I'm not aware of anything in other language ecosystems.
Cool. The other thing is that we got, as I mentioned, would not commit signing also be a good thing? And would that help? What do you think?
Yeah, so everything helps. We've got we've been going through this pandemic, and I don't know if it was common in Germany or other places where there was this idea of the Swiss cheese model, where no part is perfect. Like masks are not perfect, distancing is not perfect, washing hands is not perfect, right? No drugs were perfect. Yet if you combine multiple pieces of Swiss cheese together, the chances that something can get through all of the holes becomes much less. And so with commit signing, it definitely is an improvement. It's not like a solution on its own. So I think a lot of the things in terms of detecting bad packages or bad updates, it's like a multi-factor thing to look at. For example, is it a new author? Is it two-factor authentication enabled? And is it signed or not is another one. Because certainly in the early days, packages which are published and signed would be in the minority, and attackers are generally going to go for the low-hanging fruit. So it's good, but it's really just one slice of Swiss cheese in open source security.
So it's a general thing, right? With the security, every layer helps, right?
Yeah. Exactly.
Yeah. You talked also about Go modules a lot. And we had a couple of mentions from the audience, also from the moderation team. What do you think about Rust? And what do you think about Cargo? And how does it fit into the dependency manager rating?
Okay. So I have a little bit less familiarity with Cargo than I do with the Go modules approach. My understanding is that it adopts a fairly traditional approach to dependency resolution, where it is an optimistic resolution. So it uses ranges, and if well, at least if you specify a range, it will always try to pick the latest version in that range. So I think that from a security point of view, it is lacking compared to Go modules for this minimal version selection concept. It does, though, have a lock file, which pretty much everybody uses. And that certainly helps, though. That's a good part of Cargo and Rust. But from my point of view, both Rust and Go are really the two really just climbing in popularity languages among, like, I'll say, sophisticated teams and projects.
Yeah, that makes sense. And the other question that just came in is, do you see a solution to verified source code that avoids tight coupling between registry and build CI pipeline?
Yeah, so the reproducible builds project does have that scenario. So like one approach would be, if the registry had like an auto build function. So like as an example, seeing as they're both part of GitHub and Microsoft, if NPM had the ability that you didn't push your releases into NPM, that instead you said, okay, NPM, like this commit on GitHub, build it, then just like how Docker files are built, you would have this verifiability to say it definitely comes from that commit because I built it. But that's challenging because platforms also don't want to be building stuff nonstop, and you've even got the cryptocurrency attackers that try to use CI for mining and stuff. So then the question was, how would you do it the other way? So reproducible builds, if you check it out, they do have solutions for that. Essentially, it's when you publish a package, it's that you have almost like commit signing, you have a sign off for it, and you have the ability to trace back to where it came from. And so then the idea is that you can't instantly know, hey, this package was built from there, but you can build it yourself and verify that you get the same outcome. The biggest hurdle for reproducible builds is actually just removing variable, like time-based data from the build. So for example, it'd be quite common that the build result will depend upon the timestamp. Like you think, yeah, I'm going to commit a timestamp. The problem is, if you commit a timestamp as part of your build, you'll always get a different result, even if you run them a millisecond apart. So reproducible builds is kind of like a lot of what they do is to say, hey, this command here that you ran is actually like time sensitive. So it's going to get a different result each time. And to remove those time sensitive ones so that the same source always produces the same the same result. The power of reproducible builds is that you can verify it, not that you necessarily always do. Because like if it's like a tamper seal, like if it's pretty easy to know something's been tampered with, people are less likely to attempt it in the first place. That's the goal. That's the goal of it.
Okay, the only registry I know, by the way, I know you can push the Docker Hub manually, but F12, for example, in the Android ecosystem, you have to provide the source, and they build it. There's no other way. And we got one last question, and how can you identify which is the greater risk, right? Do you update packages, or do you stay on the older version to not introduce something?
It's a great question. I've got like another presentation where I talk about that. Like I call it like a rock and a hard place. It's like it's like two bad choices, right? You either stay behind and you have kind of like dependency rot, dependency decay. Now the risk of that is that it is very likely that you are going to get a important CVE one day. And if you are 12 months or 18 months behind, you then have an enormous risk, because you either have to delay the remediation of the CVE while you spend days testing all of these changes between the last version you used and the new, or you risk by updating to the new version without adequate testing, because it's such an urgent security risk. I would say that one thing people misunderstand is that the risk of CVE fixes normally doesn't come from the CVE fix. The stress of it is not because of like a one-line fix for a regex. The risk and the stress is because of the other hundreds or thousands of lines of code which changed since the version you were working on before. So the goal is like don't update immediately, but I would say keep reasonably up to date, because the chances that there is an undiscovered malicious in a 2-week or 4-week old package is much lower than a 2-minute or 4-minute package. So you've reduced your risk a lot by malicious by waiting weeks, while at the same time you're decreasing your vulnerability risk dramatically, because even if you get a vulnerability, you've only got like a small update to do instead of like a year's worth update.
Yeah, that makes sense. So continuously stay up.
And there are teams in Siemens I know who do that automated dependency updating.
Yeah. Thank you very much, Rhys. That was a nice presentation.
And thanks everyone for the questions. I hope you have a great remote open source fest for the first time.
Thank you very much.